All right, hello everyone. I am just setting up right now. Give me a minute. And then I am going to start streaming. All right, and it appears that everything is in working order. Now, let's get to it, shall we? 2.5. In case you've been wondering where I've been, I've just been very busy with work. It was a fall cleanup season, so did a lot of that. Uh, As a landscaper, I also picked up a number of students, so I've been very busy between coaching and landscaping. I am taking this class in the spring, so I have about 5 weeks to get through this book, which I want to get through the entire book before I take the class. I'm also taking another class, a programming class. So anyway, that's for my double bachelor of computer science and pure math. Getting back to it, I'm going to read 2.5, and then we're going to do the equations. 2.5, truth tables for statements. You should now, in case, sorry, I'm still a little bit out of it since it's been a couple of weeks. The Book of Proof, 3rd edition, look at the video description, download it. It's free. Get the book. Get the book. It's a very good book. It's Creative Commons. Anyway, you should now know the truth tables for and, or, not, implies, if and only if. So just to review, this is and let's increase brush sizes. Yeah, this is fine. And we're gonna keep that same size. This is or. Okay, this is not. This is. These are truth table. These are truth symbols. Last one is if and only if. Okay. And let's get to it then. So now we have. They should be internalized as well as memorized. So that's something we're going to have to do. In other words, go back, restudy, remember. Now, these come up a lot. So, and some of them you can just kind of work through if you understand what's going on. Now, let's continue. You must understand the symbols thoroughly for now. Combine them to form more complex statements. For example, suppose we want to convey that one or the other of P and Q is true, but they are not both true. No single symbol expresses this, but we could combine them as, so we're saying P or Q and not P or Q. All right? Which literally means P or Q is true, and it is not the case that both P and Q are true. So this is an exclusive or, I believe, what they're saying here. So yeah, they can't be both. So one or the other has to be true, but not both. This is an exclusive or. This statement will be true or false depending on the truth values of P and Q. In fact, we can make a truth table for the entire statement. Begin as usual by listing possible true/false combinations of P and Q on 4 lines. The statement P or Q and not P or Q contains individual statements for P or Q and P and Q. So we next tally their truth values in the 3rd and 4th columns. By the way, if you're following along, I know this is very complicated, but page 48. This is it doesn't get any easier. It really helps to work through this. Listening to this stuff, it's so dense that it's almost impenetrable. You have to work through it. You have to put pen to paper. Just my own aside here. Continuing from where I just stopped reading. Let's see here. The 5th column lists values for not P or Q, and these are just the opposites of the corresponding entries in the 4th column. Finally, combining the 3rd and 5th columns with and, we get the values P or Q and not P and Q in the 6th column. So, basically, this is what's happening. I know, I kind of blurb through that. Listen, this stuff is very dense, very impenetrable. You have to just kind of keep along with it. but you have to do it. This is the kind of stuff that just listening to it, you would take like 10 hours to try and memorize this stuff. You really got to sit there and write it out, and then you're going to get a feel for it. And the other thing is you don't need to fully understand what's happening. You just have to get the formulas right. That's okay. And I tell my students the same thing in skating, like especially adult skaters. Tell them, listen, you don't have to have the most thorough understanding of the biomechanics of skating. You just have to do what you're training to do, and then you could philosophize about it later if you want. But the thing is, a lot of this stuff, you don't need a perfect understanding. You just need a cursory understanding, and then just do the work. Do a lot of the work. And then afterwards, it'll all make sense eventually. It'll click. But don't wait for it to click to start doing the work. Otherwise, it'll never come. That's what I'm trying to get at. Okay, so TTFF. So we're going to say true, true, false, false. So this is our basic one. Then we're going to go with true, false, true, false. Okay. Let me see here. We have, so with P or Q. Now, this is not an exclusive or, so it could be one or the other or both. So that's going to be true. So in that case, let's see here. This is P or Q. And then if P is true but Q is false, still true. If P is false but Q is true, in the or case, it's true. What if both are false? Well, then it's false. All right. So then, did I skip one? Oh, yeah, it looks like I did skip one. Hold on. I'm going to have to move this a little bit. And move it again. Yeah, that's good. All right, yeah, back to writing. So that was P or Q, P and Q, P and Q. There we go. Okay, so now they both have to be true. If P and Q are true, both statements are true, then it's true. If one of them is false, it's false. If the other is false, it's false. And if they're both wrong, well, it's still false. Okay. Now, not P and Q. So we just reverse this. So not this thing, right? We don't want that. So whatever is the opposite of that, false, true, true, true. Cool. So now we're doing good. We're doing good. Let's look at what we have here. Now we have this right here. And okay. So we're gonna take two things. We are gonna take P or Q, and this one, and we're gonna say where do they both agree? Both are true. Okay. So very simple. Now, okay, so we have true, false. That is false. And we have true and true. That is true. True and true. That is true. True and false. That is false. All right. Now, I do have this chart in front of me. It's page 48. But what I'm trying to show you is how to work through it. You know, instead of just throwing the thing on there, I wanted to kind of just go over it and understand how these things are assembled, because you're going to be assembling these a lot. You're going to have to be able to throw together truth tables all the time. This is proofs, after all. Okay, anyway, continuing on. Now we've finished the truth table. So this is an exclusive OR, at least as I understand it. So we have P or Q, but not P and Q. So for instance, if P is true and Q is true, 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 but we say they cannot both be true, false. That's an exclusive OR. So, and then if they're both false, it's false. So one has to be right, either P or Q, but they cannot both be right. All right? That's important. So that's an exclusive OR. All right, let's continue on. This truth table tells us that P and P or Q and not P and Q is true precisely when one, but not both P and Q are true, so it has the meaning we intended. Notice that the middle three columns of our truth table are just helper columns and are not necessary to parts of the table. In writing truth tables, you may omit such columns if you are confident about your work. Yeah, for our purposes, no, we are not going to omit any columns. We're going to do the extra work because, maybe at the end of the book, we might omit a couple of these columns if it's something very tedious and simple, but generally, yeah, no shortcuts here. So we have, for another example, consider the following familiar statement about real numbers, x and y. The product of x times y equals 0 if and only if x equals 0 or y equals 0. So if x times y equals 0. Now, this should also be true, of course, if both are 0. But this is saying, okay, the product x times y equals 0 is if and only if x equal, and this is not an exclusive or. The way we normally use the word or, we normally mean one or the other or both. That's just like, in a sense, we use it as exclusive or. It depends upon how you use it. So it's kind of tricky. This is like semantics that I'm dealing with here, the semantics of the English language. But in this case, the way the statement reads, the product of, let's just throw the statement on here. Okay, so I'm just going to write it simply. We're going to say x, y equals 0 if x equals 0 or y equals 0. So basically, yeah, 0 times 0 is still 0. If one of them is 0, then it's guaranteed that the result is going to be 0. But this is not exclusive. In other words, if they are both 0, it will not be not 0. It'll still be 0. Okay. This can be modeled as, okay, x, y, this is getting more interesting, equals 0 if and only if x equals 0 or y equals 0. If we introduce letters p, q, and r for the statements, x, y equals 0, x equals 0, y equals 0, it becomes, we're going to say, which one's p here? P, if and only if Q or R. Okay. And you can kind of see what's going on. This is that statement, that statement. So there we go. So we just transfer that. We assign them to the characters P, Q, and R. So pretty straightforward, I think. All right, now notice that the parentheses are necessary here, for without them we wouldn't know whether to read it as P if and only if Q or R, or P if and only if Q or R. So yeah, just parentheses are important here. Now we're going to make a truth table for this. Okay, so we're going to go, now when you have, okay, this increases, I believe, by the power of 2. So for instance, if you have just P and Q, okay, if you just have P, right, then it's binary. It's true or false. So you can have P can be true, P can be false. If you have P and Q, then there are 4 possibilities. When you go to R, there's 8 possibilities. So it's 2 to the power of n, where n represents the number of statements that you're working with. So in this case, P, Q, and R are 3. So n being 3, 2 to the power of 3 is 8. By the way, that's just something that I just, back of the envelope, just pulled it together. I'm sure it's in the book somewhere, but I just noticed the pattern, and it just, but if you think about it, it makes sense. The number of variables increase by fact. For every variable, it doubles the number of possible variations between them. So All right. A lot of the stuff that I ramble on, I'm not a math teacher. I am a professional landscaper / handyman, and I'm a figure skating coach. So I'm also a Westchester University student in pure math and computer science. I did not pass this class, so I'm retaking this class again, and I didn't pass it because I had to focus on work. So as you can see, this is what my modus operandi is. Why I'm doing this is because whenever I get slammed with work, of course, when you run your own business, you have to put your clients above everything else, above any of your own needs. That's just the way it works. Your students, your clients come first, always. But what happens then is that I still want to develop this because I am frenetically curious about everything, and I just have this need to keep learning, I suppose. Anyway, so this is why I'm taking this class, and I still want to master it just because I find it very interesting. All this stuff, I find this incredibly interesting. I'm not one to rest on any laurels, if you know what I mean. Okay, now let's do this. True, 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 true. By the way, the order of the trues and the Fs, you can write them in any which way. You can go TF, TF, TF. But the reason why we do it this way, and then you'll see it, it's just an easy way to organize things, easier than the alternative, which would kind of randomize this. So we're going to say this is going to be half as many T's, and we're going to switch this to false, false, true, true, false, false. Okay, good. And then we're going to say this is going to be true, false, true, false, true, false, true, false. Okay. So far, I believe we are looking good. All right, good. So now we're going to say Q or R. So when we look at Q and R, if they are both true, now this is not an exclusive OR, so we're going to say yes, they're true. If one is true, then it's still true. If the other is true, still true. If they're both false, it's false. If they are both true, this is true. If one is true, true. If the other is true, it's true. If they both are false, false. Okay, good. Now, if and only if Q or R. So at this point, the reason why we did this is the one that we really needed. So now we're going to take the P, this one, we're going to combine the two of them. So we're going to say if, in other words, P implies Q and Q implies, these two have to be true. So this is going to be true. So this is going to be true, 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 false, false. So it has to work both ways, if and only if. So then we have false, true. I tend to write slanted. So then we have P again, false, true, false, false, true, false, 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 true. Now this is it's just kind of one of those quirks you got to remember. When you have an if and only if, and they're both false, it kind of says something to the effect that it can't be disproven because it was never challenged to begin with. Like, for instance, you will pass the grade if and only if you take the final exam. And if you didn't take the final exam, you didn't pass the grade, but the condition was never challenged, therefore the statement was never falsified. That's how you can think about it. Again, not a math teacher. I could totally be describing this. I know it's generally correct, but there could be little quirks or nuances that I'm missing. So keep that in mind. I'm a student. Anyway, continuing on. All right, so yeah, we fill the fourth column using our knowledge of the truth table for OR. Finally, the fifth column is filled in by combining the first and fourth columns with our understanding of the truth table for if and only if. The resulting tables gives the truth and false values of P, if and only if, Q, or R, for all the values P, Q, and R. Notice that we plug in various values for X and Y in the statements, X and Y have various values. So, in other words, yeah. So, yeah, I'm going to keep reading here. It's going to explain what I'm... Obviously, the thing that is probably in the back of your head. If we took P and Q and R, if they still mean everything that they mean over on this side. So, basically... they have to be zeros. So the fact that if, say, x equals 2 and y equals to 3, then, and that equals to 6, that does not challenge the if and only if statement with the zeros. In other words, this is a statement that has nothing to do with the original statement, therefore it does not falsify the original statement, therefore the original statement still stands. That's what it's trying to say. Anyway, okay, for example, if x equals 2 and y equals 3, then p, q, and r are all false. This scenario is described in the last row of the truth table, where p, if and only if q or r is true. Likewise, if x equals 0 and y equals 7, then p and q are true and r is false. The scenario described in the second line. There's a simple reason why p, if and only if q is true for any values x and y. It is that p, if and only if q and r represents x times y equals 0, if and only if x equals 0 or y equals 0, which is a true mathematical statement. It is absolutely impossible for it to be false. So, yeah, this makes you wonder about the lines of the table with p, if and only if q or r is false. Why are they there? The reason that p, if and only if q or r can also represent a false statement. To see how, imagine at the end of the semester, your professor makes the following promise. Okay, so yeah. Again, well, I mean, like, I didn't read ahead of this part. It's just that, like, the examples that I used were examples used in previous chapters, and just, they're doing the same thing here. So their example is, you pass the class if and only if you get an A on the final, or you get a B on the final. This promise has a form of P if and only if Q or R, so the truth values are tabulated in the table above. Imagine it turned out that you got an A on the exam but failed the course. Then the professor lied to you. In fact, P is false, Q is true, R is false. The scenario is reflected in the sixth line of the table. Indeed, P if and only if Q or R is false, i.e. it is a lie. Okay, I know this is all very dense and probably very impenetrable. You got to hit the book and just write them out. Write out whatever the book tells you to write. You don't understand it, just keep working through it. You want to start at a chapter you understand. Like, in my opinion, even for like a high school student, if you're to start at the very beginning chapters, it's pretty straightforward. If you read it and you try to understand it, you'll get it. This stuff does get more denser, but it's not like one of those things where it's just like, I mean, like, as bad as what we're dealing with here, this isn't like, I don't know, like some of the integration formulae or something like that, or even trigonometry, I think, in some ways is less intuitive than some of this stuff. Like, logic is meant to be at least somewhat intuitive. You know what I mean? Just by its nature. Anyway, the moral of this example is that people can lie, but true mathematical statements never lie. That's an interesting thing. So I had this professor, fun story. Anyway, he wanted to debate whether or not 0 is part of the natural numbers. This has to do with set theory, and this is something he debated about when he was younger. And he felt that 0 belonged in set theory, in the natural numbers. But then if you look at the way it's organized, like 0 is technically not in the natural numbers, it is in the whole numbers. So in the integers, it is in the next set. So it's one of those things, like sometimes math makes assignments to things where, or if you go with, say, factorials, 0 factorials is 1 or something like that. Some of the things, they have to be assigned in order for the math to make sense, or like saying that the definition of a prime number, like 1 is not prime. A definition of a prime number is any number that's divisible by 1 in itself. Again, I'm a student. I'm sure there's some professors that are tearing their hair out right now with what I'm saying here. But generally speaking, what I'm saying is there are things in math which are just like assigned, and they have to be that way for the rest of the math to work. So in that sense, like when we talk about what is the truth of math and what is absolute God's honest truth kind of a thing, well, see, for me, like when I think about it, like I'm not a mathematician by any means, but even I have seen things where it's just like this stuff has to work a certain way. Does it represent how the universe itself is made? Maybe, but some of the structure might be, well, not quite. Like, what is math? What is the nature of math? Is everything at its base mathematical, or is math the only thing that we can describe things they're most fundamental? It's this kind of a thing where it's just like it's a very I guess philosophical point, but I do understand that it is something worth studying. Math is just absolutely fascinating to me. Anyway, continuing on. But getting back to what I said earlier, the true mathematical statements will never lie, in the sense that something that is defined as true in math by the axioms of math will remain true within the axioms of math. But there are things that could be true or false or undecidable, and math can never truly be complete. And this goes back to Cantor's incompleteness. I think it was Cantor that did that. Or is it Gödel? I'm sorry. I got to look up on math history, really. But yeah, the incompleteness theorem is what you have to. Actually, I'll just tell you right now who did it if you want to read for yourself. Gödel did the incompleteness theorem, and he showed that no matter how many axioms you add to math, there will always be statements that are true but are unprovable, or that exist outside of the axioms of math. Anyway, it's very interesting stuff. Okay, we close the section with a word about the use of parentheses. The symbol not is analogous to the minus sign in algebra. It negates the expression it precedes, thus not P or Q means not P or Q, not P or Q. In the not P or Q, the value of the entire expression is negated. So, in other words, it's like this. Look, we're going to say not P or Q is equivalent to not P or Q. Okay? So that's how it works. It only applies to the value that it's attached. If you wanted the whole expression, for instance, we can go not P or Q, which you can be thought of is, again, not P or not Q. So there. So that's how it works. It carries over just like a minus sign would, the function of it. All right, let's continue. So now we're going to do some exercises. Okay, write a truth table for the logical statements P or Q implies R. All right, so there's going to be 8 of them. So we're going to go with this is good practice. So what do we need here real quick? We're going to need P, Q, and R. And then we're going to need Q implying here. Okay, make this R. Move this back so I have more room to work with, basically. Q, P, Q, and R. We're going to need Q implies R. And we're going to need P or Q implies R. Okay, so first I need a quick refresher. What does the implies truth table look like? All right, and so implies, we can look at that one on page 44, and I'm just going to write one right here real quick. P and Q. Just going to write a quick, simple truth table for just 2 variables. P implies Q. Let's say achievement. True, true. False, false. Say true, false, true, false. Page 44. So, is true. If P is true but Q is false, it is false. If P is Q, so fundamentally what we want to know is we have the effect. Is the effect true? P is a cause and it implies the effect. Well, if the effect still happens, then we don't really care if the cause is true or not. So in the second line, the effect didn't happen. Q is the effect. No effect, we don't care if the cause was true, because the effect didn't happen, it makes it false. In the third line, the effect happens, but the cause was something else. But we don't care, we only care about the effect. That makes it true. And if neither the cause is true and the effect is also not true, then the whole statement has not been challenged, therefore it remains true. Okay? Now let's do that. Let's continue here. P, so we're going to do our P values. True, 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 true. False, 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 false. Okay, true, false, true. No, get a little ahead of myself there. True, true, false, false. True, true, false, false. True, false, true, false, true, false, true, false. Okay? Now, we're going to say P, or between Q and R, it's the same as the implies one that I had drawn, the smaller one. So we just need to know what the effect is. The effect, if R is true, the whole thing is true, basically. And if both of them are wrong, it is also true. Okay? So it was between Q and R. So we're just going to get those out of the way. And then we're just going to look at any R's that are true. True, false, true, true, false, true. Okay. So then, now we have P or. So we are doing the or effect. So one or the other or both have to be true. Between P and Q implies R. All right, so first one is true. P is true. Q implies R is false, so that's true. Third line, true. Fourth line, 2, 3, 4, also true. Fifth line is true. Sixth line is false because they're both false. Seventh line is true, and eighth line is true. Okay, I believe that is the correct form, but we have to check the book. See what the book says. Answers are in the back of the book. We are only doing odds, so we don't damage the integrity of the book as a teaching tool. 2.5. Okay. True. Okay, so fundamentally, we only care, just to be clear, we only care about this part, right? That's what the question was. And yes, the book agrees. I can go through and check all the other tables to make sure it looks, just by like glancing at it, it looks correct. But short of like some error that I made and missed it, it doesn't look like I made any major errors. The important thing is the final result. The final table was correct. Therefore, I was just the rest were done correctly. Otherwise, I wouldn't have been able to reach that. Unless I would have taken me more than one mistake, in other words. That would have had to result in the same correct, two mistakes negating each other sort of situation. Okay, so that's good. We're off to a good start. All right, let's go line up for our Nobel Prizes. Well, we have not P implies Q. Okay. So we just did P implies Q, right? So we just have to negate that. But let's do the work, right? Around here, we don't slack. PQ, we're going to say P implies Q, and we're going to say not P implies Q. Remember how not works? It has to apply to the whole thing. Okay. There is only two statements. Regardless of how many ways we mix and match them, there's still only two statements. Therefore, there could only be 4 variables. 2 to the power of n, in this case n is 2, so 4. So we're going to say true. Let's lower that a little bit so it'll be easier to read. True, true, false, 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 true, false. When they are both false, the statement remains true because it has not been challenged. Only when the result, remember, we care about the Q, not about the P. That is true. This is false. This is true. Okay. And the inverse of that, it's going to be false, true, false, false. Okay? Alrighty. That was not too hard. If I got this right. False, true, false, false. Yep. All right. Book agrees. And this was number 3. Okay. Next. Okay. We have P and not P or Q. Okay. Okay. I have to think about this for a minute. Okay, so it has to be P and its inverse. Okay, cool. Well, let's just do that. So we're going to need P, we're going to need Q, we're going to need not P, and we're going to need P and not P, and then we're going to need P and not P or Q. We're going to need all of those. So that's like 6, I think I said. Let's do that. Let's write them out. P, Q. Actually, not. No. Not P, Q. No. I'm going to go like this. P. I'm just doing this to make it easier for me to read when I have to do this. And you can organize them any which way you like. Doesn't matter as long as the final result is correct. I'm going to put Q over here. I bet the book is going to go P, Q, then not P. But I like it this way because right now I'm just going to work through the P's. And then we're going to go to the Q. And then we're going to establish what is the final. P and not P or Q. All right? So we are going to go true, true, false, false. Now, this is the one thing with putting the Q out there. I'm going to still want to fill in the Q. Oh, the secondly, true, false, true, false. Now, the inverse of P, false, false, true, true. Where do they both agree? They don't. There is because one is the inverse of the other. They can't be an and. So an or would work. If it was or, then they would all be true. But because it's an and, they're all false. False, 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 false. So we're going to say or Q. So the first half of it we know is false. So whatever happens, we have to, it simplifies it in a sense. We know that we can't get any truth out of it, therefore we're going to worry about our Q, our or. So we know Q is true in the first and the third lines. So true, false, true, false. Okay, that's how I'm reading it. Let's see what the book says. All right. All right. Yeah, the book agrees. Okay, good. All right. And that was number 5. I hope you're having as much fun as I am. Seriously, though, if this feels dense and impenetrable, You have to put pen to paper. You have to start at a chapter that you could semi work through, and you got to work through these equations. The retention rate from my own experience of just listening to lectures is maybe like 10%, 5%. It's very, very hard to understand this stuff just by listening to videos. You have to be right there writing. Even if you're watching this, I hope that you're pausing the video and copying down what I'm doing, or you're doing it in the book. I mean, if you're just listening to me for the sake of like banter and things like that, yeah, I get that. I listen to my own videos when I work sometimes. I enjoy that. But it's just one of those things. You have to put pen to paper. There's just no other way to do math. I mean, I suppose there are. I mean, I'm not gonna say the absolutely no possible way. Stephen Hawking, like people like that. Although, I think that although he was essentially paralyzed or wheelchair bound for the longest time, before that he was physically active. I think he was on the rowing team actually. But all that aside, it doesn't mean that you physically can't do math inside your head. It just means that for the vast, vast majority of people, you have to write it down. You have to do pen to paper. You have to make mistakes and work your way out of it. That's just the practical aspect of math. So now let's just do this. We have P, we have Q, we have not P, we have or. So we have 6 again. All right, so let's do that again real quick. So we're going to say P. This time I'm going to put Q right next to it. PQ, we're going to say not P. We're going to say P and not P. And we're going to say P. Now, right away, you're looking at this thing. Okay. Yeah, I'm going to show you something real quick. Okay. We're gonna take a little bit of a shortcut, but we're going to still do the whole work. And you're going to see what I mean in a second here. Not P implies Q. Hang on a minute. Yeah, there we go. P and not P implies Q. Okay. So I'm going to show you a quick shortcut we can kind of take, which if you start doing this, you can be like, yeah, okay, I could see that. Okay, we know that. I'm just going to take a quick shortcut and say, let's just write Q in there. First, we're going to get P, and then so we're going to say true, true, false, false. We know that if it's P and not P, they all have to be true. Right? It's the universe then. So it's the item and its converse. And then the Q is going to be true, false, true, false. So then we can just take the second column of Q and the fourth column of P and not P, and then we're going to see which implies Q. Although, honestly, if I had put Q further, it would have made more sense because we care about the implication of the effect. And really, in that case, Q is going to be like this. If Q is true here, we care about the effect, Q. Effect didn't happen, effect happens, effect did not happen. And then we'll just fill in the not P first. I mean, so I saved us a column. But again, like looking for these kind of shortcuts, I mean, if you do like, I don't know, like 20, 30, 50 of these kind of equations a day, yeah, I guess you're going to start taking shortcuts. But it's like to save yourself a column wouldn't really be worth it in the grand scheme of things, because spending time looking for shortcuts, you're just as likely to miss something important and having to double back and fix it later. So anyway, let's see what this looks like. All right, so we have P, we have not P, we have Q. So then we're going to say P and not P, all are true, implies Q. And again, when it's implies, we care about the effect. We care about the Q. Effect happens, effect didn't happen. Effect happens, effect didn't happen. Okay? I believe that's what the correct answer is, but we're going to double check. All right. Actually, I may have made... Yeah, I got this one wrong, and I'm going to see why. So, Hang on a minute. So this is this is great actually. This is really good. So remember how I said about looking for shortcuts and making a big mistake right there? So, okay. A minute. Do that one more time. So yeah, I should have taken the slow and steady approach rather than trying to speed through this. Okay. So, and has to be, again, this is not an or, this is an and. So in the previous one, if we went back with, on 5, we had P and not P, P and not P, right? So, what happens is I just blew right through it. Hey, what do you know? You speed through things, you might make a mistake, and it can cause a satellite to crash into Mars. Anyway, not my problem, not yet anyway. But now you know why you don't want to take shortcuts and you want to take your time. Okay. Just as the previous one, which we already got this right, is there are none where P and not P they are agree. Okay? It's one or the other, but not both. So now, giving that, we are going to look at the implies. So when we care about the Q, but there's one more rule. Remember, when it's implies, if both the cause and the effect are false, the statement is unchallenged. It remains unfalsified. Therefore, it remains true. That's important on implies. Remember that. Implies, if there are two falses, the statement is unchallenged, therefore true. So that's important. We care about the effect. Q is true in the first line, so that's true. In the second line, both statements are false. It remains unchallenged. It's true. In the third line, Q is true. In the fourth line, both statements are unchallenged. Therefore, it remains true. Okay? Double check that again. Okay, now that has been corrected. Good. Now, in this case, what they did was they just made 4 lines. If you look at the back of the book, I made 5 lines. I wrote the not P. You really don't, I guess you don't have to do it. I like to write out every single variable. I guess if you were doing like 4 and there'd be 16 lines, oh boy, that would take a while. And again, there could be much more than that. But yeah. Okay. Oh, De Morgan's laws. All right. Now we're coming up on De Morgan's laws next chapter. All right. That was 7. Those here we go. Let's do 9. All right. 9 is going to be, okay, double negative, not. We're not going to take any shortcuts, though. We're going to write them all out. And this is actually, this is the kind of thing De Morgan's laws would help you with. All right. Not P or not Q. So this is they're signaling us for the next chapter that this kind of not. There's a De Morgan's law for that's going to simplify it. It's kind of like a double negative makes a positive situation. So here we go. Let's do it, right? Let's get on to it. Let's say P Q. Let's say not P not Q. Not P or not Q. Not. That's important, by the way. The parentheses. Not P or not Q. All right. So we have PQ, not P, not Q, not P, right. Not P or not Q. No, wait a minute. Made a mistake. This does not need a parenthesis. Not P or not Q. Yeah. The parenthesis goes away because we don't have that extra not there. I mean, I could throw it around the whole thing, I guess. Whatever. Let's do it this way. That's fine. Okay. True. True. False. True. False. True. False. Okay. Not P. False. True. What? No, what are you doing? False. False. True. True. Okay. That's right. Now. Q, not Q. False. True. False. True. Check these, make sure. This is important. If I can not mess this up, the rest should be okay. This is like the tedious simple stuff, but it's very important not to make any mistakes here. Otherwise, it sets off your whole thing. That's right. Okay. So we're going to say not P or not Q. So in this case, one or the other. But let me check on or one more time. If it's not P, if both are true, I believe it's false. I believe, let me do that. If we have or, if both, no, actually, well, that's fine. That's the thing is, this is not exclusive or. I believe if and only if is the exclusive or. But basically, if P is true, I'm looking at page 48, by the way, just a simpler. I just needed the really basic again. If you have P's and Q's, if both are true, P and Q and P or Q are both going to be true because the or is not exclusive, even though it's kind of like an and at that point. But whatever. That's fine. Here we go. Just keep that in mind. So we will have P and we have Q. Right. They both agree. That's true. And if one is true, it's true. If the other is true, it's true. If neither are true, it's false. It's not an if and only if situation. So in this case, that's fine. Now we're just going to not this. And we're going to flip everything. True. False. 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 All right. Let's check the book. All right. True, false, false, false. False, true, true, yeah. Yeah, all right. Yeah, the book agrees. All right, good. All righty. Now, 11. Suppose P is false and that the statement R implies S. Oh boy. So we're doing 4 variables. That's 16 lines. Okay. All right. But I'm guessing this is not going to be too difficult. They probably want us to understand what this says. Suppose P is false. Okay, so we're going to say suppose P is false and that the statement R implies S if and only if P or Q is true. Okay, find the truth values of R and S. This can be done without a truth table. Okay, so we know that. So what happens? P is false. So we know is P is false. So if Q is false, then P or Q is false. Oh, I see. This is going to be a situation when this is a situation, this kind of question is, it doesn't matter if Q is going to be true or false. The result should give us the same truth values for R and S. That's fine. So we have P is false. So Q can be true or Q can be false. So all right, let's say that now remember on an if and only if this statement is false, let's just say if Q is false on an IFF statement, this would mean whether it's true or false, it doesn't matter. It would be the same result as long as they're all false across the board or truth across the board. So if that's the same, R implies S. So S should be true, I think. No, wait a minute. All right, so let me think about this for a second here. If R implies S, this is a good question. I don't know. I'm really tempted just to write out the truth table and figure this out. If I don't have this bulletproof, I'm just doing the truth table. You know, screw it. I'll write 16 lines. P. Okay, so we have. Let's say if and only if. So if this is both false, R implies S. If this is false, then that statement is true. Okay. So P implies S is false. P implies S is false only when... Okay. So if this statement is false, that means that the P has to be true and the Q has to be false. Right, so then that means the S has to be false and R has to be true. I believe that's how it should be. So let's say this for a minute. So we have R is true, but S is false, so this is false. So if that's the case, so we're going to say, so we're going to say R implies S. We're going to say R, this is true. This is F. So then the whole thing, it gets an F. It's false because the effect didn't happen. But on an if and only if situation, if this is false, P is false, and we're going to say Q is false for now. We're assigning this. So then this is false. So the whole thing is true, right? So because it's an if and only if, remember that. That's important. So now we just have to reverse the P is set. We can't do anything about the P. What if the P is still false? And then I'm going to write this down here. We're going to say P or Q. This time we're going to make Q true. So this statement is now true. All right. This has to be true. And the way this could be true is if S has to be true. Hold on. No, I'm not doing this right. Suppose if P is false, then the statement is true. So this is true. Okay, P or Q. Right. P or Q is true if... Oh, no, 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 no. P or Q. Wait a minute here. Let me see here. If P or Q... If P is true... No, it's not or, it's and. Okay. All right. Sorry. Got to focus here. That's where I kept getting thrown off. This is P and Q. Okay. So if P and Q, the only way that P and Q are going to be true is if... Okay, so I actually messed up a lot of stuff here. Let me correct this. P and Q, they are both true only when they both have to be true. They can't have one F. So the F is guaranteed. In the P and Q situation, the P is set to be false. Therefore, this statement right here, this is going to be false. There's no getting around it. There is no other way that, because P is false, it doesn't matter if Q is true or false, this result cannot be made true. So this will be false, no matter what we do. We have determined that the whole statement is going to be true. So the only way that can be true is that the R implies S has to be false. Okay? And the way that's going to be false is the S has to be false. The whole thing has to be false. So, let me see here. So the implies S has to be false. And the whole thing has to be false. Now, if they are both false, that would be true because it would be unchallenged. So, this is, by the way, this is a single implication. This is a double implication. That both being false is true applies to both of them. So in this case, the R has to be true. R has to be true. So we would say that, in conclusion, R is true. And then we're going to say, so here we go. R is true. S is false. Find the values of R and S. Okay. I believe that's the correct answer. Let's find out. R is true, S is false. Yeah. Okay. Book agrees. It goes into detail just as like I worked through it the same way. It goes and just like explains how by locking in, I'm just gonna do it one more time in case you didn't quite get it. The P right here is false, right? That locks this part up. We can't do anything about that. That's locked up. That means that on an AND, now if you look at a any basic truth table on an AND, they both have to be true. So if the whole thing, if P is false, Q can be true, Q can be false. In this case, the only variable that can flip back and forth for the whole equation to remain true would be Q, which Q can be true or false, because that will not affect the falseness of P and Q. The P makes it false regardless of what Q does. We know that the whole statement remains true, and the way, because the first part is false, or second part, P and Q is false, this has to be false, because two falses will make a truth on an if and only if statement, or on an implication statement, basically. So therefore, we have to find an implication statement where this gives us a false result to make the whole thing true. I know this is probably still just like brain melting stuff. I get it. But yeah, it's fun. It's a lot of fun, and yeah, try it out. Just do it. Get the book. Start writing. It's a good book. Study this stuff. All right. Well, that wraps it up for this chapter. We got through it somehow. Anyway, that's it for tonight with this. I might stream a bit more, but a different book perhaps. All right. I hope you enjoy this video. Thank you and have a good night.